In the previous video, you saw the logistic regression model. To train the parameters w and b of your logistic regression model, you need to define a cost function. Let's take a look at a cost function you can use to train logistic regression. To recap, this is what we had defined from the previous slide. So your output y hat is sigmoid of w transpose x plus b, where sigmoid of z is as defined here. So to learn parameters for your model, you're given a training set of m training examples, and it seems natural that you want to find parameters w and b so that at least on the training set, the outputs you have, the predictions you have on the training set, which I'm going to write as y hat I, that will be close to the ground truth labels yi that you got in the training set. So to fill in a little bit more detail for the equation on top, we had said that y hat is as defined at the top for a training example x, and of course for each training example, we're using these superscripts with round brackets with parentheses to index into different training examples. Your prediction on training example I, which is y hat I, is going to be obtained by taking the sigmoid function and applying it to w transpose xi, the input for the training example, plus b. And you can also define zi as follows, where zi is equal to w transpose xi plus b. So throughout this course, we're going to use this notational convention that the superscript parentheses I refers to data, be it x or y or z or something else, associated with the ith training example, associated with the ith example. Okay, that's what the superscript I in parentheses means. Now let's see what loss function or an error function we can use to measure how well our algorithm is doing. One thing you could do is define the loss when your algorithm outputs y hat and the true label as y to be maybe the squared error or 1/2 a squared error. It turns out that you could do this, but in logistic regression, people don't usually do this because when you come to learn the parameters, you find that the optimization problem, which we'll talk about later, becomes non-convex. So you end up with an optimization problem with multiple local optima. So gradient descent may not find the global optimum. If you didn't understand the last couple of comments, don't worry about it. We'll get to it in a later video. But the intuition to take away is that this function L, called the loss function, is a function we'll need to define to measure how good our output y hat is when the true label is y. And squared error seems like it might be a reasonable choice, except that it makes gradient descent not work well. So in logistic regression, we will actually define a different loss function that plays a similar role as squared error, but will give us an optimization problem that is convex, and so we'll see in a later video becomes much easier to optimize. So what we use in logistic regression is actually the following loss function, which I'm just going to write out here, is negative y log y hat plus 1 minus y log 1 minus y hat. Here's some intuition for why this loss function makes sense. Keep in mind that if we're using squared error, then you want this squared error to be as small as possible. And with this logistic regression loss function, we'll also want this to be as small as possible. To understand why this makes sense, let's look at the two cases. In the first case, let's say y is equal to 1, then the loss function y hat comma y is just this first term, right? And there's a negative sign, so it's negative log y hat if y is equal to 1, because if y equals 1, then the second term 1 minus y is equal to 0. So this says if y equals 1, you want negative log y hat to be as big as possible. So that means you want log y hat to be large, to be as big as possible, and that means you want y hat to be large. But because y hat is this sigmoid function, it can never be bigger than 1. So this is saying that if y is equal to 1, you want y hat to be as big as possible, but it can't ever be bigger than 1. So it's saying you want y hat to be close to 1 as well. The other case is if y equals 0. If y equals 0, then this first term in the loss function is equal to 0 because y, 0. And then the second term defines the loss function. So the loss becomes negative log 1 minus y hat. And so if in your learning procedure you try to make the loss function small, what this means is that you want log 1 minus y hat to be large, and because there's a negative sign there. And then through a similar piece of reasoning, you can conclude that this loss function is trying to make y hat as small as possible. And again, because y hat has to be between 0 and 1, this is saying that if y is equal to 0, then your loss function will push the parameters to make y hat as close to 0 as possible. Now, there are a lot of functions with roughly this effect, that if y is equal to 1, it will try to make y hat large, and y is equal to 0, it will try to make y hat small. We just gave here in green a somewhat informal justification for this particular loss function. We'll provide an optional video later to give a more formal justification for why in logistic regression we like to use the loss function with this particular form. Finally, the loss function was defined with respect to a single training example. It measures how well you're doing on a single training example. I'm now going to define something called the cost function, which measures how well you're doing on the entire training set. So the cost function, j, which is applied to your parameters w and b, is going to be the average, really, 1 over m of the sum of the loss function applied to each of the training examples in turn, where here y hat is of course the prediction output by your logistic regression algorithm using a particular set of parameters w and b. And so just to expand this out, this is equal to negative 1 over m sum from I equals 1 through m of the definition of the loss function above. So this is yi log y hat I plus 1 minus yi log 1 minus y hat I. I guess I can put square brackets here. So the minus sign is outside everything else. So the terminology I'm going to use is that the loss function is applied to just a single training example, like so, and the cost function is the cost of your parameters. So in training your logistic regression model, we're going to try to find parameters w and b that minimize the overall cost function j written at the bottom. So you've just seen the setup for the logistic regression algorithm, the loss function for a training example, and the overall cost function for the parameters of your algorithm. It turns out that logistic regression can be viewed as a very, very small neural network. In the next video, we'll go over that so you can start gaining intuition about what neural networks do. So with that, let's go on to the next video about how to view logistic regression as a very small neural network.